Learn another name for it in chapter 5, but for now it's a double replacement. So you just switch partners. Okay, HOH is just H2O. Okay, and then imagine I wanted you to find the, I'll get a different color here, mass of this produced, and I'm going to give you, I'll even make it crazier. Okay, just a second. It takes me a minute to make stuff really crazy. 1.0 grams, let's say this is 1.0 grams. And let's say we did the experiment and found out that we resulted in 0.0020 grams of this. Okay? And now I want to know the percent yield of the sodium chloride. So that's my question. What's the percent yield of the sodium chloride? Okay? This is a limiting reactant problem. Does anybody know why? Not only because of the title I gave you a second ago, but because I'm giving you information about more than one reactant, and that information will lead to moles of both of those reactants in this case. Because of that, it's called overspecified in math. It's going to give us two answers, which chemically we'll be able to rule out one of those two answers. Okay, so here's what we do. We are going to do these one at a time. We'll start with whatever one you want to start with. We'll just start with HCl. It was first in the reaction. Then I'm going to use a periodic table to change this to moles. And I think that would be 36.45 grams per mole. Oh, by the way, you need to make sure this is balanced. And I think it all is, but always double check that your equation is balanced. Then you would say, well, there's 1 mole of NaCl for every 1 mole of HCl. So in this case, it wouldn't cause a mathematical change. And then we would want, I eventually need to find, we need the molar mass of sodium chloride, so we can change that to mass. Okay, I'll calculate that in a moment. Okay, let's do the same thing. I'll get a different color pen. We're going to do the same thing for sodium hydroxide. Okay, so that's 1 gram of sodium hydroxide. Change that to moles. Okay, I also need that molar mass. If anybody has it, you can just yell it out. And then there's 1 mole of sodium chloride for every 1 mole of sodium hydroxide. And then the last step, again, I'll need the molar mass of sodium hydroxide. Okay, let's find all this stuff. Okay, does anybody have the molar mass of sodium hydroxide on them? Beautiful, I knew somebody was on this. 39.998. And did anybody find that for sodium chloride? The molar mass. 58.35. There we go. 58.35. And somebody is already way ahead of us, so I will get your number next. So there's all the numbers from the periodic table. Okay, I'm ready. You have one of the answers? You have this answer? Or this one? So you can just make this stuff up at home with your friends. Come on. For the color, 1.58 grams, and this is of sodium chloride. And did anybody do the second one? And 1.458. Okay, we'll just keep a bunch of digits for now. All right, now I have 2 answers, which is mathematically possible with what was given, but chemically not possible. So which one's the correct answer, top or bottom? The smaller answer, which will be the bottom one. Okay, that means the limiting reactant in this case is what? The sodium hydroxide is the limiting reactant. So I'll start. That means the HCl is called in excess. There's too much of it. Okay? So this one, because there was less of it, produced less amount of product. Okay, so that's your typical, if they ask you what's the mass of the product form, you do both stoichiometric calculations and pick the smaller number. Now, for our question though, they want the percent yield. Well, to get the percent yield, I'm going to take what was given, mean found experimentally, which is that number up at the top right-hand corner, and I'm going to divide it what was theoretically possible according to my calculations. I'll multiply that by 100, and it'll change me into percent. So let's try this. Again, percent yield is going to be the actual or experimental. So this is how much was actually obtained, divided by what was calculated. We just found this number, 1.458 grams. We're going to multiply this number by 100%. Okay? Okay, did anybody happen to find that? And this will be my answer. How many sig figs will I need, by the way? Just 2. 4.14. So a high school student must have done this. It's such a terrible percentage. Okay? 0.14. Oh, even worse. A junior higher. Did we say 1.4? Okay. Okay. An elementary school student. There we go. Cool? So, not always, but it's not unusual to have a percent yield problem coupled with a limiting reactant problem. Okay, any questions on this? So you're going to do 2 stoichiometric calculations, pick the smaller number, and if there's more questions, solve that afterwards. Yes?
So to find the percent yield, you want to use a smaller number all the time?
He said to find the percent yield is a smaller number all the time. It's the given number all the time, which should be smaller. If it's not smaller, you've probably messed up. Meaning, whatever you calculated, if that's the smaller number, you probably made a math error. So go back and just double check your math that you calculated. Yeah. So it's always, again, the number in the numerator is always the given number, which better be the smaller number. The number on the bottom is also always the number you calculated, which better be the bigger number. Okay, let's look back on what we're doing. We're rolling here. I love this. Okay. Let's do molarity. If you look through, again, looking through practice exams is always helpful. You get to see what I pretty much always have it on exam. I don't think I've ever not had a molarity long answer question, at least for the past like 5 or 7 years. Okay? So I've always included something about molarity because it's just a key thing you're going to have to use over and over again. So for molarity, remember that it's moles per liter. There's 3 types of calculations that you can do with this. The first one is a conversion type of calculation. The second one is a dilution. And last one is stoichiometry. Okay? The first one and the second one involve one compound of interest. The third one will involve a reaction, so multiple compounds. So that's how you tell the difference between the first 2 and the third one. Again, the first 2 only involve one compound of interest. Now, to tell the difference between the first and the second one, molarity and volume will be changing. So if you see molarity and volume changing, you know it's the second one. If you see molarity and volume not changing, it's the first one. Okay, so that's how you differentiate the first 2. All right. So there's a lot of exciting examples that have been given for this one. Let's take HF, aqueous. What's the name of this, by the way? Hydrofluoric acid. Hydro, again, because there's only 2 elements. Hydrofluoric acid. Okay, for this one, let's say I have 5.0 molar hydrofluoric acid. And let's say I have 100 milliliters. Okay? Now let's try one example where I want to know, well, given that information, what's the mass of HF? So what's the mass in grams of hydrofluoric acid? Okay, This is what category?